but hopefully that's okay. So the next talk will be by Rob Zellem, who is a research scientist at JPL. Rob will be talking to us today about Exoplanet Watch, utilizing small telescopes operated by citizen scientists for transiting exoplanet follow-up. Go ahead, Rob.
Thanks, everyone. And just to double check,
sorry, one moment. You're in the presenter view. So.
That was my next question. Thank you. Let me see how I can switch displays there. Now, are you seeing the full screen?
Yeah, awesome.
Great, thank you. And thank you everyone for having me, really appreciate it. And sorry, I'm a bit flustered today. So I'm here to talk about Exoplanet Watch. And this is a really fun citizen science project that I've been working on at JPL through the Exoplanet Exploration Program Office and through Universal Learning, which is a NASA SMD funded project to basically do citizen science outreach to the overall community. So presenting today Exoplanet Watch, which is inviting citizen scientists to observe transiting exoplanets. And as you probably are all aware of, TESS is a great mission in the sense that it will be discovering thousands of transiting exoplanets. It's predicted to discover at least 1,250 planets in this two-minute cadence images, but potentially, according to Barclay et al., might discover 10,000 plus. Right now, we know about 3,000 to 4,000 exoplanets, so TESS will greatly increase our largest population of exoplanet targets. And that's great for future missions like Hubble, James Webb, Ariel, and an Astro 2020 mission, which will be observing up to 1,000 planets with Ariel. However, if you want to observe all these 1,000 exoplanets with Ariel, or even tens or hundreds with Hubble or James Webb, you need to know exactly when your transit will occur. If you want to observe a transit to characterize the atmosphere of these exoplanets, we have to know exactly when that transit will occur. And we need to keep things fresh. We need to keep these mid-transit times, these ephemerides, fresh as possible. So if, for example, I'm writing a Hubble proposal or James Webb proposal, and I think my transit occurs in the dashed red, but it actually occurs a little bit earlier or a little bit later, I run the risk of completely missing that transit event. So if a transit has a 15-minute uncertainty, that's an extra 15 minutes of observation time we need to build in terms of overhead to our observing scenario. And while that doesn't sound like a lot of time, 5, 10, 15 minutes times 1,000 planets, that starts getting into a lot of time that we're quote unquote wasting by trying to make sure we hit that transit perfectly. Also, that directly translates into less science that can be achieved by large telescopes, James Webb, ground-based telescopes. So the more accurate I know my transit timing, the more efficiently I can use my large telescope, therefore enabling additional science by those large platforms. But luckily, this is where small telescopes can come into play. We've recently written a study that came out a few months ago this year that indicates that small telescopes as small as 6 inches or even 3 inches are actually capable of observing a statistically significant population of the currently known transiting exoplanets. So on the right is actually a 6-inch telescope from Tucson, Arizona that observed HAPI-32b. This is a relatively dim hot Jupiter, 11.3 Vmag. The tracking was actually not even that great. The target slewed across the focal plane by 300 pixels. So despite this being a relatively dim star, despite the less than perfect tracking, despite this actually being a robotic telescope, we were able to get a really, really nice high precision science grade transit out of this small telescope. And by looking at this data set from this telescope, which is a micro observatory telescope, which is run by Harvard CFA in Tucson, we did some forward modeling to estimate the ability for small telescopes to achieve additional science. So if we look at the currently known exoplanets, the current 3,000 known transiting exoplanets, we project that a single 6-inch telescope on the left and the right can actually observe on the order of 200 of the currently known exoplanets. That's nearly a transit every single night that a single 6-inch telescope could observe. And if we then do forward modeling to estimate the impact on timing saved, we get these plots up here. At the top is the cumulative time saved for about 188 targets that can be observed by a 6-inch telescope. And we're estimating that that single telescope can save on the order of 10,000 days, assuming a certain target population. If we remove those targets with large uncertainties in the data, which are those vertical jumps on the left panel, we get something more conservative, about 10 days. So that's still 10 days of additional science that can be basically given back to missions like James Webb, Ariel, and Astro 2020 Decadal mission. On the bottom, we took the next step. We said, let's assume we now have a network of 16 6-inch telescopes. And if we run the same simulations again, we can see that now this small, relatively modest-sized network of small telescopes can actually save these missions on, conservatively, on the order of about 100 days. And that's a lot of science that could be achieved with that time. Repeat observations with small telescopes also would enable us to achieve additional science cases. So for example, repeated observations with these small telescopes. This can be done because these small telescopes can repeatedly observe these targets many times without having to worry about other science cases. We could also monitor for things such as TTVs, transit timing variations. And by seeing how the mid-transit time varies from epoch to epoch, we can directly infer the measurement or the discovery of a new external exoplanet. So you can actually discover new planets using just a network of small telescopes. And potentially, we can actually measure the masses of some of these planets. And if you want more details on the actual forward modeling and predictions we were able to do for this small network of telescopes, definitely take a look at our paper. It's Zellem et al. 2020, and it's in PASP on Archive and ADS. Repeated observations of the same targets also allows us to monitor for stellar variability. Variability of the host star can actually directly impact and change the measured transit depth of the target. And that can actually, in some cases, drastically change your interpretation of the atmospheric physics in that planet's atmosphere as well. And small telescopes are actually used in a paper by Brian Kilpatrick. He's a postdoc at Space Telescope. In that paper, we were able to determine that the variability seen on the exoplanet was not induced by the host star. That was all from a relatively small ground-based telescope out in Arizona as well. Small telescopes also provide us the ability to search for blended pairs. So on the left is that single 6-inch telescope. Its plate scale is higher spatial resolution than it is for TESS. So on the left, we can see those two stars are quite clearly resolved. But since TESS is looking over such a wide field of view, its plate scale is a lot larger. So those two stars become one. And that blended pair effectively dilutes the transit depth. So something that you think is a super Earth or a small or a Neptune-sized planet actually might be a Jupiter-sized planet due to the dilution of that transit depth by that binary star companion or the nearby star companion. So a single 6-inch telescope can actually provide some really helpful backup and target vetting of TESS. Keeping all these science cases in mind, and keeping in mind that small telescopes, particularly those run by amateur astronomers, we decided to build our own data reduction code. Actually, yeah, right here, let's go here, called Exotic. So this is the Exoplanet Transit Interpretation Code. This is a Python transit reduction tool, so it's completely written in Python. And what this does is this takes raw FITS files made by amateur astronomers and completely reduces them. It does multi-object photometry, it takes care of your calibrations, it does atmospheric fitting for air mass variations, and it also does a full statistically significant model fit to your data. It actually uses a nested sampler to fit Mendel and Engel model light curves to the data. And this code actually will work on any multi-object or even single object photometry data. So if you have data from a telescope that's in photometric time series, you can use this to go from your raw FITS files to a fully modeled and fitted light curve, as I'm showing down there in the bottom right, that was actually made by Exotic. And we actually published these papers, these figures based upon this reduction code. And because we're using an nested sampler, we're able to fully reduce the data in about 10 to 15 minutes. And that's on a standard Mac laptop. Another cool thing about this project and this code is that it's able to reduce the data in real time. So at the top right is actually data taken from a 6-inch telescope, and Exotic is actually able to produce a really quick and dirty light curve reduction of the data. So this allows you, for example, if you're at a star party and you want to observe a transit, showing that to the public is kind of silly because it's just a photometric time series. It's hard to see that 1% dip in the transit depth over time. With Exotic, you can actually point to to your computer screen and say to someone that's walking by your laptop or your telescope to say, look, we're observing a transiting exoplanet right now. And you can point to it and talk about exoplanets. So we're really hoping that people will start adopting and using this tool to reduce their data in real time at star parties. If you want to, we actually have it completely up on GitHub right now. We're getting very, very close for the launch and release of the software. It's at github.com/rzellem/exotic. And we should be launching an official version of this code, hopefully in the next month. And then this is basically getting back at the whole point of Exoplanet Watch. So given that small telescopes are capable of making high precision observations, and we now have this data reduction tool that is fairly user-friendly for even novice users of computers to use, we now are starting this project called Exoplanet Watch that will tie together a network of amateur astronomers with small telescopes to observe any transiting exoplanet. They take their own observations of a target. They then reduce their own data. They then upload their data to a server. And every day we automatically scrape that server with our own reduction pipeline to immediately publish all of our values every single night. So all of our values, all of our reductions are completely available and public for anyone and everyone to use. So there's nothing stopping anyone from using our data products and writing a paper on it or publishing it or using it for their own observing planning as well. If you want to start looking at our website, we have yet to launch. We're still in beta test phase. We're hopefully launching in the next 1 to 3 months. Just Google NASA Space Exoplanet Space Watch, and we should be one of the top websites that come up there. If you're interested in participating, if you have a telescope, that'd be great. If you don't have your own telescope, we have a way to get you data as well. Just send me an email or just contact us through our website as well. So thank you so much for your time, and I'll take questions if there's any.
Great talk. I was told the clapping didn't last as long as it should have. So hopefully that makes up for all the past presenters who didn't get enough clapping. So that was an awesome talk. It's awesome to hear small telescopes doing big science. There's a question in the chat, so I'll go ahead and start with that. From Stephen Kane, he says, thanks, Rob. Exoplanet Watch is a great project. With so many possible targets, do you perform any kind of prioritization or otherwise take requests for high priority atmospheric follow-up targets?
Yes and yes. So we prioritize using our own ranking algorithm targets that we think that are very likely to be observed by missions like James Webb, like Hubble, but also those targets that have large uncertainties. And it happens to prioritize targets that have bright host stars with bigger transit depths. And then, yes, we definitely want to offer this as a tool for the entire community to use. So if there's a target that you really want to observe with James Webb or Hubble, but your ephemerides uncertainties are too large, send us an email, get in touch, and we'll be happy to have our network help observe that target for you.
Awesome. So I have a question. So 6 inches is like pretty small aperture size. How faint can you go, and are there other networks of, I guess some people have larger telescopes, but kind of what's the array of sizes there, and yeah, how faint of targets?
Yeah, it sort of depends on the host star brightness. So I don't have the plot right here on hand, but our sweet spot we're getting, actually no, there's on the bottom left of this plot, some of these telescopes, a single 6-inch telescope can get down to 15th VMAG potentially. So that's a 3 sigma detection on the transit depth itself. We have some users that also have 14 and 16-inch telescopes, but we really are trying to focus on making this project as accessible to as many people as possible, and by doing so, keeping the costs down. So a 6-inch telescope is a lot more cost-friendly than a 16-inch telescope. But we were pretty amazed to figure out that you could actually potentially observe some of these targets For context, TESS is expected to discover planets in the 10, 12 mag mode area. So that's only great for these small telescopes.
Awesome. There's another question from Paul Dalba. Really awesome, Rob. Does or will Exotic have a means of stitching together photometry from various sites spread out in longitude? I'm thinking about long period planets with long duration transits.
Yeah, and that's actually something we're looking forward to doing as well. So there's another sort of flavor of exoplanet watch called ExoClock. That's basically the Ariel's mission, the Ariel mission's version of exoplanet watch that they're running out of Europe. And we've already come to an agreement to collaborate with each other, and also for these long period targets to potentially look into the future of handing off observations. So if a transit starts in Europe, they can hand it off to the US as sort of arises on our coast as well. Exotic, ostensibly, there's nothing preventing you from stitching multiple data sets together. We do a plate solve solution, we align all the images. So I'd really actually love to try this out. So if you have a data set, I would love for you to download it and let us know and get us feedback as well. That would be really cool.
Awesome. I'm getting some questions in the chat. Just a reminder, if everyone could post the questions in the Slack, but I'll go ahead and ask one of them. Have you thought of citizen scientists across the globe? This would enable more TTV coverage for each target. So I'll add on top of that question, how are you reaching out to amateur scientists?
Yeah, exactly. So we actually have a lot of people mostly in the Western Hemisphere, and then people that are in Europe have typically been going to ExoClock, but there's nothing precluding anyone anywhere from joining either or both of our projects. Mostly it's been word of mouth right now. I've been giving lots of talks to amateur astronomy clubs, to YouTube channels and other things like that. When we officially launch in the next few months, we'll hopefully do a big press release, but it's open to anyone and everyone, those with telescopes, those without, and regardless of where you live in the world. As much coverage as we can get, the better.
Awesome. Well, thank you again for a great talk. Let's move on to the next talk. So